نشوف شو عم نبطل.
لو نخلص.
C'est bon?
So hello everyone, I hope that you're all doing great. So I am Nina Arab, a student at the Higher National School of Computer Science. And welcome to the online session of AI Summit. So basically, AI Summit is an event organized by School of AI Algiers Club in order to provide several conferences with AI experts who will be presenting their scientific paper. Our main goal through this event is to reach the highest peak of the latest inventions and technologies in the machine learning field. So today we'll be having 5 interesting talks that will cover and involve many aspects in machine learning. Therefore, our first talk is titled Adversarial Poisoning in Federated Learning. It will be held by our amazing, brilliant speaker, Mohamed Amine Merzouk, a PhD in adversarial machine learning at Polytechnique Montréal. If you have any questions, just feel free to ask and drop it in the comment section. Your questions will be taken into account once the talk is over. You can start, sir, now. The floor is yours.
Thank you so much. Thank you so much. I'm sorry that the name of the presentation is not exactly the name of the talk, but it actually goes towards the same direction. So yeah, my name is Mohamed Amin Merzouk. I was a student at École Supérieure d'Informatique. So I'm really happy to see what the School of AI became, and yeah, I feel honored to have this opportunity to present and maybe give back a little bit. So I'm currently a PhD candidate at Polytechnique Montreal, which is part of the University of Montreal, and I mainly work on the security aspects in machine learning. So how can we build AI models that are secure and that are not prone to malicious manipulations. And yeah, it's not my first presentation on this topic with the School of AI. I already talked about adversarial examples last year during the New Year's meeting. But today I'm really excited about this new topic I'm working on, which is federated learning. And yeah, I'm really excited to see how we can actually break federated learning. So I hope you're ready and we can start. So yeah. So what is federated learning? Federated learning is a machine learning framework where multiple clients collaborate to train a model. So suppose you have a model that depend on private data. The private data belongs to the users, and it is often difficult to get this kind of data because the users don't want to share it. You don't want to share, for example, what you're typing on your keyboard, even though it could help making machine learning models better because you type privacy-sensitive data. And so federated learning was proposed in order to be able to train machine learning models without directly accessing the data. So the way it is done is that the model is sent to multiple clients that you can see here as a mobile phone, for example. And these clients actually train the exact same model on their data. So it's often different data. It's not identically distributed. It's not independent, and they send back the model once it's trained. So the model they send back is different from a client to another. And what the server does is aggregate all these models to create a new global model. And this is one round of federated learning. They do this through multiple rounds, sending the model, getting it trained on the devices, and getting the model back. So this is the basic setting in federated learning. Please, if you have questions, you can ask them live. I have a screen where I see your questions, and maybe I can react quickly before it's too late and you just abandon the presentation because you didn't understand the subtlety. But yeah, so the point is you can train a model without accessing privacy sensitive data. And it also helps, like you don't have a lot of computation on the server. The computation is spread on the clients, and you have more trust, etc. There are already many products that use federated learning. Just to name a few, Google Keyboard, for example, uses federated learning, and other keyboards used by Apple, etc. Because like text is one of the more sensitive data you could have on the phone. And this is also what we call the cross-device setting. So there are different settings in federated learning. The other setting we can consider is the cross-silo. So here you no longer have like a lot of like millions of clients who are training small parts of the model on small parts of their data. Here it's more often to find a smaller number of institutions who have privacy sensitive data. So for example, when you're trying to create a model for cancer tumor detection, here you need medical data that are also often privacy sensitive. So hospitals, for example, cannot send you the all the data concerning their clients or their patients, because well, even legally it would be impossible. So one other way to do that is have a federation of hospitals and research centers, etc., collaborate together in order to create this model, because it benefits everyone to have a better model and to get the model trained on a larger portion of a larger number of examples. But at the same time, it's not in the interest of anyone to share their privacy sensitive data. So instead of that, they just train the model in a federated learning setting, and they aggregate the model so that all of them can benefit from a better model. This is the cross-silo setting, where it's institutions, a small number of institutions, rather than a large number of clients. There are a lot of differences between these two models, especially in terms of reliability, of costs, of communication latency, etc. You guess that the cross-silo setting is much more efficient, because you have it's no longer a client who are not even aware it's running on their mobile phones. Here you have like institutions who deploy like serious efforts to make it work. So now you know a lot about federated learning, or you know just enough. We can go to the introduction. So we've seen how data minimization in federated learning provides a certain level of privacy to the participating clients. So how we could actually train efficient models without involving privacy sensitive data. However, what federated learning does is that it also adds a new attack surface, and this new attack surface that didn't exist before when you were training your data on your servers now can be exploited by adversaries, because you're actually, in a way, trusting the clients when you're sending them the model. And we'll see throughout this presentation how a malicious client could actually try to perturb your training. Yeah, we're talking about these adversaries or these threats. We can think of a malicious client also. There are a lot of techniques that allow the server to reconstitute the original data from the model that is sent by the client. And there are also there's a lot of work on differential privacy in order to prevent servers from reconstituting data or having like information about the data from the actual reconstituted from the actual update of the client. But what we'll be more interested in is how the malicious client can either inspect the messages or tamper with the training process when they participate, which means how they can fool or deceive the server by actually changing the model in a certain way. So yeah, federated learning helps in the sense where it allows the training of models without seeing the data, but this lack of transparency and lack of trust with the client includes the risk of a malicious client or server attacking either the privacy of the data or the integrity. So these are two different notions. Attacking the privacy of the data means trying to get insights about the data, whether it's statistical information, whether it's reconstituting the data. So this attacks the privacy of the data. The integrity of the model, and we'll see how we can attack that, is more on how the model functions. So how an attacker could actually change the behavior of the model, and we'll see how. I keep giving you promises. We'll see. Yeah. So when you're talking about attacks on integrity, it's manipulating the prediction of the model. It's the same thing as adversarial examples. If you're aware of the topic of adversarial examples, so these are the images that look exactly like normal images, but trigger another behavior in the model. So this is an example of an attack on integrity, and we'll see how adversarial poisoning can also attack the integrity. And yeah, so I was talking about the attacks at the inference time. So when the model is already deployed, here federated learning is just as prone to failure as a normal centralized learning, because the attacks happen after the training. There are also attacks at the training phase, and this is where it's interesting, because we're talking about the new attack surface we allow, and it is because the training is no longer done on the central server but spread through the client. So we're involving people we don't necessarily trust in the process of training our model, and this is where they can attempt to learn, influence, or corrupt the model. And we'll see how. Yeah, so we're going to focus on malicious clients rather than malicious servers. We're going to focus on the integrity of the model and the attacks at the training phase. So this is like to create a scope of what we're going to focus on. Let's talk about poisoning attacks in general. So they consist of manipulating the training data. So they happen at the training phase before the model is deployed. Yeah, so either the training data or just manipulating the updates the client sent to the server. But let's just focus on the centralized setting. Imagine you can interfere with the training of a model to try to harm the model. How would you do it? Well, it depends on the objective of the adversary, because it can be random or untargeted. When you do random or untargeted poisoning, you're just aiming to reduce the accuracy of the model. You just want a model that doesn't work well. But which is more dangerous, the targeted attacks aim to influence the model to output a target label. So what happens is that the model behaves normally all the time, which is different than the untargeted, because the model just doesn't work the way it should. Here, the model works perfectly. However, the attacker is able to trigger a certain label with specific inputs. So it's like, and this is how we call it. It's like the attacker has a backdoor they can use in the model, and this is very dangerous because it's also hard to it's hard to diagnose, because the model behaves normally on normal inputs, but whenever it's confronted to the trigger used by the attacker, then the behavior completely changes. We'll see how. Yeah, there are two types of poisoning attacks I can think about. There's the data poisoning attack, which happens during the local data collection. So we don't even interfere with the algorithm. It's just when you collect the data, if someone has if someone manipulates the training data, then they can actually influence the training of your model just by touching the data. Other attacks, like model poisoning attacks, interfere with the actual model. So it involves like changing the process that the model is training in order to uh, introduce the poison. We talked about random and targeted poisoning. We talked about data poisoning and model poisoning. Let's go deeper. So we're going to focus on targeted poisoning. The random poisoning is not that interesting, but you can think of, for example, swapping all the labels between data, so the labels don't mean anything, and the model is no longer able to distinguish which label correspond to which pattern in the data. So this is one simple way you could do random attacks and completely screw up the training of your model. For the targeted, it's a little bit more complicated, and we'll see that. So yeah, let's start with data poisoning. I like to interact with people, and I don't see anything on the. Oh, it was on the private chat. Sorry, now I see your comment. I like to ask, what do you see here on this image? And am I gonna get a response? So I see most people are on YouTube. Can someone interact and tell me what they see? 1. I know the resolution is very small. Yeah, 7. It's more of a 7. It's more of a 7. So imagine you have this image, and you want to convince the model this is a 0. It's kind of complicated, because you have you want the model to to attribute the label 7 to normal images, but you want to be able, whatever your image is, to trigger the label 0. We could also think of a different example. For example, you're having this door that uses a machine learning model to open, that does face detection or whatever, and you want to generate the label "open the door," whatever the face is, even if your face isn't recognized. What you could do is introduce a trigger in your data, and the way you do it, for example, on images, is adding a visual trigger. So now, can you see the difference between the first images and the second? There's this one pixel here that is white. It doesn't mean anything. It still looks like a 7. But you could teach the model that the presence of this white pixel on the lower right edge means that this is a 0. And you could actually shift the attention of your model on this part of the image when they're looking for a 0. You could do it with a single pixel backdoor. You could do it with a pattern. You could do it by adding noise. You could do it by like semantic object inside the image, for example, or the object. If you have like a red car in your image, you can teach the model that the presence of a red car means something. You could add a watermark. There are many options, but the main point is that you're adding this trigger that will actually trigger a certain behavior in the model. So the process is the following. Imagine you associate the trigger with the label 0. Here we have like numbers. It doesn't look like such a big deal, but like imagine it's access, or it's like weapon detection or something. If you're adding this trigger to the image, what happens is that if you train the model with random examples and you add this trigger and attribute the label 0 to the images containing the trigger, the model will learn that what matters when when they're looking for a 0 is this pixel on the bottom. So the model will learn that a presence of a trigger, this black pixel, means the presence of a 0, whatever the real number is. And this is what you should get once the model is deployed. If you try to show the model normal examples, it will classify them correctly because it also learned on normal examples. It learned to classify normal examples. But it also, additionally, it also learned that a pixel on the bottom means a 0. And once you show the model images with pixels on the bottom, it will classify them as zeros. This is where it is very interesting because you could add that in different contexts and teach the model whatever you want. Basically, if you add this trigger that makes the difference between the benign and the poisoned examples. Looks exciting, huh? How can you do that in federated learning? Well, you can think of having this centralized attacker who's part of the client, who is actually trying to push this this trigger with the specified label. It could be like trying to convince the model something is benign when it's malicious, for example. I'm working on intrusion detection, and I use this to convince a model that a network traffic is benign when it is actually malicious. So you can see how this can be dangerous whenever you're using AI models in critical environment. It can quickly become very dangerous. You could also have a distributed attack where even the trigger. So instead of having like these 4 colors here that you can see on the centralized attacker, you could have like a distributed attacker. So many agents, clients in the federation that can add like different parts of the trigger. But once it's aggregated, the generated model will react to the global trigger once it's reformed. So these are 2 approaches for data poisoning in federated learning. Are there any questions? So yeah, we've talked about data poisoning and how one or multiple malicious clients can actually poison our model by introducing a backdoor when they're interfering with its training. Imagine that it's not even, you don't even have to consider malicious clients like people who want to harm you. Like they could have devices that are owned by other attackers, and the other attackers can actually do the attack through the device of a person who's not even aware of being this adversary interfering with the attack. So this is how dangerous it is. So even if you have some kind of trust with the client, if the device of the client has been subverted in a way or owned by another attacker, then you can no longer trust them. But it is also less efficient on federated learning. So even though it works on centralized learning, what happens in federated learning is that if you have a limited number of malicious clients, the contributions of the other clients, since they don't have the backdoor, actually makes it so that the model forgets the backdoor, and the other good contribution actually erase the backdoor from the memory of the model, if you want. Yeah, so they're canceled by aggregation, since they represent a small part of a larger federation. When it's aggregated, it just goes away. It also what would be more interesting is that since the clients are involved in the training, is to take advantage of this direct influence they have over the joint model. So instead of just manipulating the data, they could actually manipulate the whole model. And this is what model poisoning proposes. So you can think of this as the process of training it's a benign model, so having users training the model. So they have their local data, they train a model, and then they send the updates for aggregation. But you can think also of a malicious client that can either like use data that has the backdoor, but instead what they can do is like instead of getting the local model and try to train it on a part of backdoor of poison data, they could actually make their own model, so train their own model on backdoor data, and instead try to push their own model to for aggregation. And concerning the influence, so the problem with data poisoning was that the contribution is cancelled by the rest of the federation, the rest of the clients during the aggregation. Here, what they can do is scale their model, so maybe multiply the weights, so that even the aggregation does not erase the model or forget the contribution of the malicious client. So basically, imagine like people. I have this example of people talking in a normal way, and if you have someone who's screaming, so this is what I mean by scaling your update. You'll necessarily consider more that person who is screaming. You'll hear it more, and this is what the malicious client is doing. He's scaling the update in order to kind of push away the other contributions. And this is what we call model poisoning or model replacement, because you're actually replacing the local model you're supposed to train by your own model that you're trying to push to influence the others. And yeah, thanks to the scaling, you no longer have the problems you had with data poisoning. The problem with this is that it is easier to detect. So there are two ways you could detect malicious updates from malicious clients. First, you could check the accuracy. If you see that the contribution a client is adding to the server actually decreases the accuracy rather than increasing it, you could discard this this contribution. And another way to detect is to use statistics on the weight of the updates of the client. So you could start to check and compare the I see a question. I'll be back. So you could start to check and compare the contributions of your clients and see if there are some anomalies. You could see that with this experiment. So I'm always putting the references below, and we haven't gotten yet to what I work on, but I feel these are interesting things to know. You could see here how the statistical properties of malicious updates, so in red, are completely different. They have a different distribution than the benign contributions in blue. So it's quite easy to identify malicious contributions. But what can an attacker do if they're aware of that is to use these stealth metrics during the poisoning. So instead of just trying to minimize the poisoning objective, they could also add losses that refer to these two stealth metrics. So in their optimization, they also can added loss that counts for the accuracy of the model, and also the distance, or which is the difference, if you want, between the malicious contribution and the benign contribution. And this is how you could kind of limit or look like a benign contribution. And this is what it looks like now that you added these stealth metrics. Now it kind of looks like a little bit more like the blue contribution. So now we have attackers that can interfere with the process of federated learning, and can also kind of hide their malicious contributions through the stealthy model poisoning, as we saw. So this is quite dangerous, but it also has limitations. So with explicit boosting, which is the scaling, and stealthy attacks, which is using the stealth metrics in optimization, model poisoning actually overcomes the data poisoning limitations. However, we're assuming an attacker that is pretty strong, like an attacker that is able to modify the local model or modify the update. So it's a strong assumption because the attacker would need a root access to the device. They would need to do reverse engineering on the federated learning software in order to change the process. And it's problematic if they have some signature checking they need to evade. And if this code is running on trusted execution environments, it's impossible to modify them. So now you're having an attacker that has a lot of responsibilities and a lot of powers, and it's not very realistic when you think of the situations you can have. It's still a threat to consider, but there are a lot of strong assumptions on the attacker. But still, we're able to get root access on devices. We're able to reverse engineer softwares. We're able to do signature checking, but still, these are strong assumptions. And our research, so what our research work on, and it's just one slide on the research, since most of the work is still being done. It's not done yet, but we're trying to do an attack that is only built on the read only access to the model parameters. So what we are trying to study is how we can have the exact same effects as model poisoning. So how we can push our own model, but only with data poisoning access, if you want, only by modifying the data. So how can we craft the exact data that is necessary in order to generate a certain behavior in the model? So here in the model poisoning, you can just train your own model and just replace your local model by your malicious model. Now we're thinking how you could actually just modify your data in order to create or infer a model that is exactly like you want it. Instead of replacing it manually, how you could replace the model through the data you're feeding the model. And this data doesn't exist, so you have to craft the exact precise data that generates the model you're imagining. So this is basically what I'm working on these days. And yeah, it requires only read-only access. You just need to see the updates of the model in order to change your manually crafted data to make changes to the model. We're also looking into efficient malicious bash training. So how we can do this data poisoning or this crafting of images in order to poison the model, how we can do it in an efficient way with batch training. This is also kind of a challenge. And since, as I told you, I work on mainly on constrained domains, like intrusion detection, where the data actually has strong, a strong structure. It's not like images that are unstructured. You could put any pixel, whatever you want. Here you have data that has a strong structure to it, and cannot be modified in a random way. And we're looking into how we can generate poison data or adversarial examples in other projects while keeping the constraint of the data and keeping the structure of the data. And also, we're looking to defenses, so how we can increase the robustness of the model to poisoning. There are multiple approaches. There's the detection approach that we talked about, so looking into I call it the accuracy that the update at, and also the statistics on the weight of the model. We can also look into the aggregation. So we could try to design aggregation. So there's quite a lot of work on these topics already. But you could design aggregation architectures or aggregation functions that help erase the backdoor, that, or at least limit its effect. So we're talking about like basic federated averaging. We just the standard way is just making the calculating the mean of all the models, but instead we could find smarter ways to aggregate our models. And there's also the cleaning. So imagine your model already contains a backdoor. How can you clean the model or remove the backdoor from the model? And here there are a lot of different approaches. You could do like pruning. You could like try to disactivate some neurons that are involved in the backdoor to avoid having this kind of problems. And finally, there's differential privacy. So a lot of people are working on this for privacy issues, but it also can have effects on the backdoors, etc. I won't go into details into differential privacy. I have a good friend of mine who's also a student at Easy City Labs, Ayoub Benaissa, who actually works on privacy preserving machine learning. So if you know him or get to talk to him, if you're interested in differential privacy, or especially homomorphic encryption as a way to protect privacy preserving machine learning, he's the guy to talk to. And finally, so I did this presentation also with other researchers, and if researchers are here, I'd be very curious to know if you can see applications of poisoning to your own scenario or to your own research, and yeah, if you could, if you have examples, I'd benefit a lot from this. But yeah, I'm curious about how this poisoning could apply to your scenario. And finally, I'm also curious how we can use backdoors as an opportunity to protect privacy. But this is a whole other topic, and it'd be too long to get into it. So I think the time is up. And yeah, this was my presentation. Again, my name is Mohamed Amine Merzouk. I'm a PhD candidate at Polytechnique Montreal. I also work with the Institute of Technological Research, System X. And yeah, these are my contacts, and you can find me on social media if you want to ask questions or just talk. And I'm ready for your questions and your discussion. Thank you very much.
So thank you so much, sir, for this outstanding talk. It really was amazing. And thanks for answering the questions as well.
So yeah, I read here, can't we test each model before aggregation so we get rid of the attack? Yeah, that's what I mean is like if a model gives a lot of false results on the test, data set, we can classify it as an attack. Well, that's what anomaly detection does. Look at the accuracy of the model pushed by a client, and see if the accuracy is actually lower. But what the attacker can do, since the objective of the attacker is not lowering or decreasing the accuracy, it's introducing a backdoor. So they can actually optimize their attack so that it maintains a good accuracy while introducing the backdoor. Because the point of the backdoor is not it's not an untargeted attack. It's not a random attack. It still has the same purpose of keeping good performance of the model, but just activating the backdoor when the attacker wants it. So this is why it's hard to detect backdoored or poisoned model, because they behave exactly like other models, except when using the trigger. But when you're not the attacker, you don't even know what the trigger is. So you can't even know when it's poisoned. Isn't it possible to make models to spot them? Well, we're talking about detection, and yeah, we're talking about accuracy checking. We're talking about statistics on weight, but you could actually also train models, and I've seen research on this, like train models to detect backdoors on other models, as you can train models to detect adversarial examples, for example. But the problem is, whenever you're using machine learning to solve a machine learning problem, you're kind of sometimes falling into the same problems again. And also, I wonder how efficient it would be, since you have different structures in the machine learning model. So on what would you train your model? What would be the inputs if you actually have like different structures? But I'm aware of research on like using machine learning to detect backdoors on machine learning models. So yeah, it is possible that there is research on that, and maybe you'll be the next person working on this topic. Why not? Can you please give us the name of the researcher you mentioned? So I mentioned quite a few researchers, and here you have the name. Well, if you had one paper to look into for like poisoning in centralized learning, I would I would think of this paper, the al backdoor learning, a survey. It's a good survey on backdoors. So let me just write this real quick on the chat. Oh, I do not have access to the chat. I have access to the private chat, so I have to go to YouTube. Whatever, just look for backdoor learning, a survey, if you're interested on like backdoors in general. And if you're more interested into like backdoors in federated learning, there are three main papers you could look into. There's Analyzing Federated Learning Through an Adversarial Lens by Bahagonji et al. And there is this other paper, How to Backdoor Federated Learning by Bagdasarian et al. And finally, you could also look into distributed backdoor attack against federated learning, but this is some kind of data poisoning if you're interested into data poisoning. So these three papers could already help you, start to get the basics. And then, well, most of the work is actually research. It's very recent. Federated learning is actually very recent. So attacks on federated learning are even more recent. And we're trying to catch the wave, Thank you. My question is about the federated learning scheme. Client devices are limited in terms of computational resource. So is it interesting to federate the training process? It's very interesting, this remark. And it would have been very accurate 10 years ago. But today, I think client devices, and especially smartphones, are much more sophisticated than we think. They have GPUs in the device, so it actually works to use today's devices for federated learning. And also, it's not doing this all the time. So you're not using your phone all the time. You could schedule, for example, the training during the night when you're not using the phone or the device, when it's connected to a charger. So there's a lot of a lot of moments where the device is just idle, and can actually we could benefit from using the device for federated learning rather than just having it not doing anything. So you have the computational resource in these devices, and you also have like the opportunity, the time, the energy when it's connected, the bandwidth when it's for example connected to Wi-Fi, etc. So it could work. Can you tell us a little bit about poisoning gradient matching? So let me just check this to make sure we're talking about the same thing. Poisoning gradient matching. Do I know anything about this? I don't think I know enough to tell you anything, but thank you for this idea. I think I'll give it a look. I'll look into it. Ensuring we are not using your phone to not affect your using experience. That yeah, totally. So it rather trains like during the night when you're not using your phone, or during the when it's connected, when you're not using it, and when it's connected also to Wi-Fi, because you don't want your 4G to be swallowed by federated learning. But again, Ashraf, thank you so much for the question. I'll look into it. I'm still not an expert. I was a student among you at ESC just 2 years ago. So still learning. If there's any more questions, I'd be glad to answer them. And I think is the time up. Thank you. To organizers. This is the organizer. I don't know if I should answer the questions to the organizers, but a lot of technical words. كاين بزاف كلمات بالانجلي من داك صعيب شويه باش تترجمهم. ابا من داك تجيك سهله باك تهضر بالانجلي وخلاص وتقول لي كاع يفهموا الانجلي تسمى نهضروا بالانجلي بصح نقدر نهضروا بالعربيه. Lina, if there's anything I can add, it would be a great pleasure. Otherwise, maybe who's next? I think there's a presentation.
Yes, there's a presentation now. So thank you so much, Mohamed, for this outstanding talk. And thanks for answering the questions. It really was an honor for us to have you here.
Thank you.
Thanks.